Hello everyone, my name is Rohit Singhal and we were discussing about the hydrocarbons. In the previous classes, I have discussed about the alkanes, alkenes and the other hydrocarbons, and in this class and the onwards we will discuss about the special and the last category of hydrocarbons, that is aromatic hydrocarbons. So, let us start with it. Aromatic hydrocarbons. Till now we have discussed a few things about these aromatic hydrocarbons, and in these classes and the further classes we will discuss in detail about these properties of it, synthetic measures of it, and how these physical properties are different, what are the structures of it. So, we will discuss them in detail. Okay. So, aromatic hydrocarbons, I have discussed one aromatic a few aromatic compounds till now. This is benzene, this is naphthalene, this is anthracene. Okay. These kind of hydrocarbons in which the benzene ring is a repeating unit. So, you must say that naphthalene the kind of 2 benzene rings are together, anthracene is 3 benzene rings together. So, this kind of compounds, for example, one also is there like this is called biphenyl. So, these kind of aromatic hydrocarbons in which benzene ring is repeating, benzene ring containing aromatic compounds, and these are called benzonoids. These are called benzenoids. Benzenoid structure this is called, and there are few aromatic hydrocarbons that do not contain any such benzene ring. For example, like this is known as furan, this is known as pyrrole, this is known as thiophene, this is called pyridine. So, these kind of aromatic hydrocarbons in which benzene ring is not present are called as non-benzenoid hydrocarbons. Non-benzenoid hydrocarbons. Okay. So, now starting now we have discussed what are the aromatic hydrocarbons. Okay. So, two broad categories, benzonoid forms and non-benzonoid forms. So, what how these aromatic hydrocarbons are special or different from those of normal alkenes or alkene structure. As you must be seeing, for example, let us take an example of benzene. Okay. So, let us try to understand the structure of it. If I will go a bit about detail of its structure benzene. So, it is around 1825 it was isolated, benzene was isolated, or so it was scientist Michael Faraday in 1825 who discovered benzene, or who isolated who isolated the benzene. But till 1825 Michael Faraday, neither does anybody else know what is the structure of benzene. He just isolated that there is a molecule called there is a molecule which has a molecular formula of C6H6. Okay. He isolated that, but the structure of benzene was still unknown, what the structure is. So, around in 1865 Kekulé proposed structure. Okay. Kekulé proposed structure to be contain alternate pi sigma bonds, and he proposed two forms. He proposed these two forms of benzene. He proposed these two form of benzenes. What he indicates, what Kekulé suggested that there are six carbon atoms, six hydrogen atoms, and carbons are in a form of alternate sigma pi double bond. But Kekulé proposed this structure, but still he gives the two structures, two possible structures of benzene will be possible according to him. But what we have seen is, when we have done some experiment of this, when we did some experiment, what we observed that okay, we know that the C single bond C is around 154 picometer, the bond length. C double bond C bond length is around 133 picometer. What we have found that C single bond C in benzene has same length, that all the 6 CC bond in benzene have same length, and it is around 139 picometer. Okay. So, VBT suggested this. Okay. What happened is ki Kekulé suggested that there are benzene structures. Kekulé gave in 1865 that there are two possible forms are possible, but Kekulé also does not know that why, how these structures are two different structures, or what will be overall structure will be represented. So, a VBT later on gives its structure. So, what Kekulé can't what Kekulé wasn't able to tell is कि when we react for example when we react something some halide or some hydrogen, something like this, to a benzene. Till now it was suggested, or it was thought that benzene has a similar structure of alkene kind of thing, and if it is so, then it will also should have shown addition reaction, but it actually does not show addition. It does not show addition reaction, unlike alkene. So, it was clear that unlike alkene, it does not show the addition reaction, rather it shows a substitution reaction. That means it is a different structure. We get to know that it is a different structure, and what we have got, that substituting to any of the hydrogens, substituting any one of the hydrogens is we are getting the same structure. That is till before Kekulé suggested the structure, it was like this, that it does not give C6H4Br2. This is not observed, that is addition product is not observed, addition product not observed, rather we got a substituted product, and only one substituted product. That means what it indicates, is all the 6 carbon hydrogen bonds are same, and according to this, Kekulé then suggested the structure. So, he suggested these two structures, two forms possible. Okay. So, this was what Kekulé told or what Kekulé explained, but what Kekulé was not able to explain was drawbacks of Kekulé structure or limitations, we can say, not drawbacks. So, what were the limitations that he wasn't able to tell, he wasn't able to define. The stability of benzene. He was not able to explain the stability of benzene, and how benzene consisting of 3 double bonds is so much stable. So, that he wasn't able to explain, but he just gave the 2 structures. Later on, theory came, that is VBT, that you will discuss or that you will actually learn in the later classes. It is known as valence bond theory. Valence bond theory. According to valence bond theory, then we got to know that what happens is that to these 2 canonical forms there exists a hybrid structure of it. There exists a hybrid structure of it that we can represent like a dotted circle inside a cyclohexane, or just a circle inside the cyclohexane. So, these are the hybrid structure of benzene, and this hybrid structure is a resonance form of the 2 canonical forms. And what happened, this due to this resonance, benzene is a stable molecule or compound. So, what happens is, due to this resonance present or due to this delocalization, that means the pi electrons, all the pi electrons are revolving around the ring. Due to this delocalization and resonance, the benzene has so much stability. Okay. So, all the 6 pi electrons the 3 pi bonds or we can say 3 pi bonds or 6 pi electrons are delocalized in the entire ring. Okay. So, that is why this benzene molecule is so much stable, and this is also one of the reason that I have already told that why CC bond length is same, because what happens is, due to this resonance form, what happens is all CH bonds are same. That is why on substitution get a single product. Second is all CC bonds are same. All CC bonds are same. It is around 139 picometer. Intermediate of, it is actually intermediate of normal CC and C double bond C. Normal CC and C double bond C bonds. Okay. So, these are the reasons that why benzene is stable, why all the CH bonds are same, and this due to this CH bonding, all the CH bonds are same. That is why on substitution we obtain only one substituted product and not others. All the CC bonds are same. That is why if all the CC bonds are same, that is why the bond length comes to be only 1 in the experimental conditions. It does not give the addition reaction, because that means there is extra stability. This extra stability comes from the resonance structures of the benzene. Okay. So, further going on, how we can we can say resonance. If we further need to, if further going to study about this benzene stability, that how this resonance structures. So, what happens is, so I have told there are two canonical forms A, B, and there exists a hybrid form like this. Okay. So, if we see, if let us take one of the canonical forms of like this, for example, B I am taking. So, if we see in the canonical form that all the 6 carbon atoms, all the 6 carbon atoms are sp2 hybridized. Okay. Okay. So, now look at, now let us look at the structure of it. While looking at the structure of it, let us take this example, that this is carbon number, this is carbon number 1. Okay. This is an sp2 hybridized carbon. 2 sp2 hybridized orbitals make sigma bond with so what happens is, this is a carbon. Okay. So, what happens is, it makes one sigma bond with another carbon using a 1 sp2 hybridized orbital. This consists of 1 sp2 hybridized orbital. Okay. And it makes another another sigma bond with another neighboring hydrogen using the second sp2 orbital. Okay. Now, we have total 3 sp2 hybridized orbital. In total, sp2 means 1 is s2 over p. So, in total there are 3 sp2 hybridized orbitals. Okay. So, better use the word here, hybridized. And what happens is, it makes one sigma bond with H using the third sp2 hybridized orbital. Okay. Using this third sp2 hybridized orbital. So, what we get, the total structure, in total structure what we have got is okay. So, sigma 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 sigma. Okay. So, these are also the sigma bonds. Okay. So, now what we have, sp2 hybridized orbital, we have what, 3 sp2 hybridized orbitals. What happened to these 3 sp2 hybridized orbitals? 2 are involved in C single bond C, and 1 is involved in, if I am talking about one single carbon. So, 1 is involved in making CH sigma bond. Now, what this sp2 hybridized also contain is one unhybridized sp2 orbital. Now, this one unhybridized sp2 orbital, what it does is, and this unhybridized sp2 orbital is perpendicular to the neighboring one. So, what it does is it makes a double bond with this. Okay. So, this unhybridized sp2 orbital that is remaining is capable enough, is perpendicularly aligned, and we can say orientically favored to make a pi bond. So, that is how a pi bond is made. So, that is how we can say there is a pi, there is a one unhybridized p orbital here, it makes a pi bond here, similarly like this, and it makes like this, and the structure we have got this we have formed now. So, what the structure we have got is C double bond C, C, C double bond C, C, H, 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 and these pi bonds can be formed in the alternate direction also, because all the unhybridized p orbitals are perpendicular to each other. So, this is how the structure of benzene can be explained. Further, we will discuss more in detail about the structure and properties in the next classes. Thank you.